Hello and welcome to this video for Chemistry 30 following the Alberta curriculum. This is the first lesson into the electrochemistry unit. So electrochemistry, we're going to introduce electrochemistry, some of the terminology that applies with it, including terms like reduction, oxidation, redox reactions, oxidizing agents, reducing agents. It's a lot of terminology that comes up in this unit that's very important to get your head around to help you throughout the unit. So we have some mnemonics that should help you to understand and memorize essentially all that terminology that happens. So let's start with a quick review of writing a net ionic equation and what the purpose of a net ionic equation is. So if you remember, we did this in Chem 20, and technically you start learning how to write reactions back in Science 10. So my following reaction is copper is placed in a solution of silver nitrate. So copper is by itself, so it's in its elemental form or its atom form, right? When elements are by themselves, if it's a metal, which in this case copper is, it would be Cu solid. Metals are all solid when they're in their atom form, with the exception of mercury being a liquid. Then I have an ionic compound that I'm mixing it with, which is silver nitrate. When I have an ionic compound, remember, we're looking up ion charges and we're balancing ion charges to write the formula for that compound. So silver as an ion has a 1+ charge, nitrate as an ion has a -1 charge, so I need 1 silver with 1 nitrate. Now this reaction, if you remember to Science 10 and Chem 20, is called single replacement. Single replacement reactions happen in solution. Of course, it also says in the question it's happening in solution. So what that means is you have to use your solubility chart to check whether or not this is soluble. And I mean, the word that it says it's a solution there means it is soluble, but you can always double check on the solubility chart. Now, in a single replacement reaction, what happens is whatever element is by itself, in this case it's a metal, is going to switch with the same type of element in the compound. So copper is going to switch with silver, okay? Now, copper as an ion is multivalent. It could have a 2+ charge or a 1+ charge. If the question doesn't tell you which charge to use, you look at the periodic table and you use the first charge listed, which for copper is a 2+. So copper has a 2+ and nitrate has a -1, which means we will need 2 nitrates to bond to our copper to make that balance. Again, solubility chart states that that's aqueous. And then the silver metal ends up by itself in its elemental form again, which again would be silver solid. So this again is just the start of writing a net ionic equation. It's not actually the net ionic equation, it's just the start. We call it the non-ionic step, okay? The next step, let's use a different color. The next step is to convert it into a total ionic equation. Now in Chem 30, when we write net reactions, we're not going to go through all these steps. We're going to learn some shortcuts on how to do it, but I just want to kind of refresh your memory with, again, how we learned how to do it last year. So what I'm doing in a total ionic is showing what do these species look like when they're dissolved in water, or if they're dissolved in water. Copper metal, metals, elements, they don't dissolve in water. They stay solid. In this case, copper metal stays a solid copper metal. However, my silver nitrate will dissolve in water. As we said, it was aqueous. And remember, soluble ionic compounds not only dissolve, they also dissociate. And actually, sorry, I just realized I forgot to balance my reaction. I need 2 nitrates, which gives me 2 silvers on both sides. There we go. Okay, so I need to show this compound dissociating into free ions. So now I have an ion form of my metal. So it has to have an ion charge present and the state is aqueous. I also have 2 nitrate ions dissociating out of that compound. Ions are always aqueous when they're dissolved in water, and that's the only way you usually have an ion is either your ionic compound is molten, which means it's in liquid form, or it's aqueous dissolved in water. Okay? Now, next I have copper nitrate. That again is a soluble ionic compound. So I have a source of copper 2+ ions and 2 nitrate ions. Okay? And then last, I have my silver metal. Elements do not dissociate. Elements do not turn into ions. The only time you have the ion form of an element is when it's coming out of an ionic compound. That's when you have the ion form. But when they're in their elemental form, they're in their atom form. They do not have a charge. Okay? So that's our total ionic. Now what we do is we cancel what we call the spectator ions. The spectator ions are the ones that are not changing in ion charge. So nitrate is starting as NO3 -1 and it's ending as NO3 -1. And they should always balance. If you balance the reaction properly, they should always balance. Okay? And then what we have left over, that finally is our net ionic. So what we have left is copper solid, what we have left of the purple reaction. Copper solid plus 2 silver ions are becoming copper 2+ ions and 2 silver solid. So what's the purpose of a net ionic equation? It is to show the change that is happening. And what is happening is copper is starting with an ion charge of 0, because when it's in its elemental or its atom form, it is not an ion. Its protons equal its electrons, so its net charge is 0. But when it's in its ion form, it has a charge. So copper now is being produced as an ion. So my copper is starting with an ion charge of 0, and all of a sudden it has an ion charge of 2+ during this process. Now remember, if you have a positive charge, this means you lost electrons. When you lose electrons, because electrons are negatively charged, that builds up a positive charge because there's now more protons than electrons. Okay? My silver, what happened to my silver? Well, my silver started with a +1 charge. That's what that symbol there means, because it starts as an ion, but then it turns into a neutral atom. So now its charge is 0. So my silver, let's actually make a different line for silver. My silver, if it's gone from +1 to 0, it's gained electrons, because electrons, again, are negatively charged. So if electrons are negatively charged and your ion charge is decreasing, that's because the negative electrons are balancing with those positive protons that you started with, and now you have a net charge of 0. So this is the key to electrochemistry. We have a transfer of electrons. Okay? One substance, in this case copper, is losing electrons. The other substance, in this case silver, is gaining electrons. All right? And that's kind of the introduction or the premise of electrochemistry. These are reactions that undergo a transfer of electrons. So obviously there's lots of potential uses for this, right? If we think of the transfer of electrons, the first thing you should think about is electricity. We can generate electricity from this process. Okay? So that's something we're going to talk about throughout this unit, the generation of electricity, batteries, electroplating, electrolysis processes. There's a lot of useful applications to electrochemistry that we're going to learn about throughout the unit. But this was just a reminder or a review again of how to write a net ionic equation. Okay? Now, we're going to get into the terminology. So we're going to start by talking about a redox reaction. And a redox reaction comes from 2 terms, reduction and oxidation. okay? So the red for reduction, the ox for oxidation. Because when one substance is losing electrons, it's undergoing the process of what we call oxidation, okay? Now there's some sayings, like I said, mnemonics to help you memorize when it's oxidation and when it's reduction. Those are the two, we call these half reactions. They're half of the reaction, and when you put them together, that gives you the redox. So we have the saying, Leo the lion says grr. So Leo stands for loss of electrons is oxidation. Now, one thing I want to bring up, I looked at ion charges before, and the actual term that we use in electrochemistry is oxidation number. So ON, short for oxidation number. This is the apparent charge of an element. Okay? So we're going to get into that in more detail a little bit later on. There'll be a lesson on oxidation numbers. But for now, you can just think about it is if I have an ion, its oxidation number is its ion charge. If I have an atom or an element not part of an ionic compound, then its ion charge or its oxidation number is 0. Okay? So for example, let's look at magnesium. Magnesium losing electrons. Magnesium is starting in its atom or elemental form by itself. So its oxidation number is starting at 0. It's turning into a magnesium atom, which has an ion charge or oxidation number of 2+. So notice what's happened to the oxidation number, the ion charge. It has increased. So when the oxidation number or the ion charge of a species increases, you have an oxidation half reaction, which is known as a loss of electrons. Now, how do we show something is losing electrons? Remember in the thermal unit, if it was losing heat, it meant it was exothermic. And when something's exothermic, it's a product. This is similar. If it's losing electrons, electrons are a product in your, we call these again half reactions. Okay? So magnesium becoming a magnesium ion is doing that by losing 2 electrons. Now, how do you figure out how many electrons are being transferred? There is a formula that we use. The number of electrons being transferred is equivalent to the change in oxidation number times the number of atoms that is going through that change. So I technically have 1 magnesium on each side, right? They should be the same on each side. I have 1 magnesium atom becoming 1 magnesium ion. So my number of electrons being transferred, the change in oxidation numbers from 0 to 2, so it's changing by 2, and there's 1 atom of magnesium on each side. So that's my transfer of 2 electrons, okay? Now let's look at another example. This oxidation process is what happens when metals form cations. Because as we know, when a metal forms a cation, right, it loses electrons. We learned that even in Science 10. But now we're actually showing the process for that and writing a half reaction out of it. What about nonmetals though? Nonmetals like chlorine. So chlorine is diatomic. Okay, because chlorine is diatomic, there's 2 atoms of chlorine that bond together to form the chlorine molecule. So I need 2 chloride ions to balance that. Okay, before I had 1 magnesium on each side. This time I have 2 chlorines on each side. Okay, now each chlorine as an ion starts with a -1 charge. Okay. And then, as it turns into the diatomic atom, it becomes 0. All right? So my number of electrons transferred here, the change is by 1, but there's 2 atoms going through that change, 2 chlorine atoms or 2 chlorine ions. So that is again a transfer or a loss of 2 electrons. Notice again how my oxidation number went up. It went from -1 to 0. Think of it on a number line. You're starting low and going high. Same with the magnesium. It was starting low and going high. Anytime your oxidation number increases, it's always an oxidation process. It's always a loss of electrons called oxidation. Okay? Now let's look at the other half reaction that takes place in a net ionic equation called reduction. Reduction is the gain of electrons. So my saying, Leo the lion says grr, that's where the grr comes in. Gain of electrons is reduction. And in that process, when you're gaining negative electrons, that's going to make your ion charge or oxidation number go down. So for example, let's say I have iron 3+ ions. Sorry, sometimes my pen makes these lines, I'm not really sure why. Iron 3+ ions are becoming iron atoms. So my oxidation number this time is going down from +3. Again, I can think of this as a number line. Okay? So thinking of a number line, we're just going 3, 2, 1, 0, -1, -2, -3, and so on. I'm going from 3 down to 0. So that means we are gaining electrons. And again, the number of electrons would be my change in oxidation number, which is by 3 this time. And again, there's one ion and atom on each side going through this change. Okay? Now, when electrons are gained, they are a reactant. Just like when you gain heat, it's a reactant. Okay? So reduction is a gain of electrons. Gain of electrons is reduction. Oxidation number, you can tell whether or not it's reduction or oxidation based on the oxidation number. Oxidation numbers or ion charges are very, very, very important here. They show the transfer of electrons. Okay? Now let's say I have bromine, a nonmetal. My nonmetal bromine is diatomic again, just like chlorine was. So when I form my ions, I have a balancing 2 free bromide ions. Ions are never diatomic. When they dissociate, that becomes a balancing coefficient. Okay? So I'm starting with bromine with an oxidation number of 0 because it's in its atom form, and it's changing to an oxidation number or ion charge of -1 because that's its ion charge. Each bromide is -1. So if I'm going from 0 to -1 on my number line, again, I'm going down. So when oxidation number decreases, that means we're gaining electrons. Electrons are a reactant. Now the number of electrons, again, if I calculate that, my change in oxidation number is from 0 to -1. So it's only a change of 1, but again, there's 2 atoms this time because, again, 2 atoms, 2 ions, whatever you want to call it, there's 2 bromines on each side. Okay? So that means I'm actually transferring 2 electrons. So that is your terminology for oxidation half reactions and reduction half reactions. Leo the lion says grr. Oxidation number increases for oxidation. Oxidation number decreases for reduction. So it basically kind of one way of doing electrochemistry. We'll learn kind of another way tomorrow. One way to figure out what's happening in your reaction is by looking at the oxidation number and the change. Okay? Now, as I said, these 2 half reactions come together and make the term redox reaction. So when you have a redox reaction, we actually show it as a net ionic equation. We're showing, again, their specific ion charges if they are a dissociated ionic compound or if they're in their elemental or atom form. We're actually showing that, and we're showing the change that's taking place. How is the ion charge or oxidation number changing? And that tells us what chemical change is happening, the transfer of electrons. Now the electron transfers must balance. So what that means is sometimes you may have to multiply your half reactions to make the electrons balance. So if I have two being lost, I also need two being gained. And we'll do some examples to look at how that works. Spectator ions, the ions that are not changing in oxidation number, are omitted. They are not part of your net reaction, your net redox reaction. Now this is where the terminology gets tricky. The substance that is being reduced or undergoing reduction is called the oxidizing agent. So it's backwards, okay? The reason it's called the oxidizing agent is because the substance that is being reduced is gaining electrons, okay? In order to gain electrons, it has to take the electrons away from the other substance. So it's causing the other substance to lose electrons. So it's causing the other substance to undergo oxidation. So that's why the reduced substance is called the oxidizing agent. And the oxidized substance is called the reducing agent. Now, I had some students several years back make up a new mnemonic saying to help you memorize this. It's called RALEO the OAGER. So we'll write this out. RALEO the OAGER. RALEO the OAGER. Okay? And so what this stands for is reducing agent loses electrons and undergoes oxidation. Or we can say it's being oxidized. Kind of like present versus past terms there. And then the oxidizing agent gains electrons and undergoes a reduction half reaction, or is being reduced. Okay? Now, this process happens when your oxidation number goes up. Okay? Electrons, when they're being lost, are a product. The OAGER process happens when the oxidation number goes down. When you're gaining electrons, electrons are negatively charged, they make your ion charge or oxidation number decrease. The electrons are now a reactant. Okay, so in this net redox reaction that you're going to write, always one species should be gaining and one species should be losing. So one half reaction have electrons as a reactant and one has it as a product. They shouldn't both be gaining or both be losing. And then just to kind of put all the notes out here, the number of electrons transferred is the change in oxidation number times the number of atoms or elements, whatever you want to call it, on each side of that half reaction. Okay? So this is a nice summary. This is something you want to memorize. This needs to be memorized, inside and out. Okay? RALEO the OAGER. You want to write that everywhere. If it's saying which species is the reducing agent, that means it wants the one losing electrons, the one undergoing oxidation. Which one's the oxidizing agent? It's the one gaining electrons undergoing reduction. Okay? Or it could say which one is being oxidized, which one is being reduced. So all those terminologies come up several times throughout the unit. So you really have to put this to memory. Okay? Now let's look at some examples of writing a redox reaction. Now it wants you not only to write the net ionic equation, but it also wants you to write the half reactions. Write and label the half reactions. Okay? You have to label which is the oxidizing agent being reduced and which is the reducing agent being oxidized. And again, step one, in order to do that, if we want to write out steps, is to identify oxidation numbers. Oxidation numbers, again, being their apparent ion charge. So I'm starting with sodium in its atom form. So it's starting with an oxidation number of 0. I'm reacting it with ionic compound lithium chloride. So that means that this will dissociate into free lithium ions and free chloride ions. So lithium ions will have a +1 charge. If you don't remember, their group number kind of tells you what charge they have, right? Lithium's in group 1, so it has a 1+. Chloride is in group 17, so it has a -1. Because for nonmetals, you go 18 minus the group number. Okay? Now I have lithium by itself, so now it's in its atom form and is 0. And then I have sodium chloride ionic compounds, so ions. So sodium ions, again, are group 1 +1. Chloride, group 17, -1. So I can actually look at what's happening here between my two species. Oh, and one other thing I should mention, my spectator ion. I can identify my oxidation numbers and my spectator ion as part of my first step. The spectator ion, again, is the one that is not changing in oxidation number. That's the chlorine, or the chloride ion. It's starting as -1, it ends as -1. So we can omit it, okay? It is essentially not being part of the net reaction. My lithium's oxidation number is going from +1 to 0. So its oxidation number is decreasing, which means this is my OAGER. This is my oxidizing agent. It's gaining electrons and it's undergoing a reduction half reaction. And then my sodium is starting at 0 and it's increasing to +1. So it is my RALEO. Okay, so again, to figure out what's happening, start with oxidation number. Start with the ion charge. If it goes down, it's the OAGER. If it goes up, it's the RALEO. Now, how I write my half reactions and label them, I'm going to say my oxidizing agent, which undergoes reduction, in this case, was the lithium ion. So I have to dissociate that and show that I have a free aqueous lithium ion, and it is becoming lithium solid. Okay? Now the number of electrons transferred, again, I have lithium starting as a +1, going to lithium as a 0. So the oxidation number change is 1, and there's 1 lithium on each side. So I'm gaining 1 electron. And in chemistry, we commonly don't show the 1s, right? So that means I could put a 1 in front of the electron, or I could just write it as an electron, and that means 1. Okay? Again, when it's gaining, the electron is a reactant. Now, my other half reaction is for my reducing agent, which is undergoing oxidation. So I write ox short for oxidation, red short for reduction. You can write the whole terminologies out if you want to, though, but this kind of just makes it a little shorter. So my reducing agent undergoing oxidation is sodium. Sodium is starting as an atom and turning into a free ion. Right? It's turning into sodium ions, dissociating out of that ionic compound. Now, sodium oxidation number is starting at 0 and is going up to +1, so it is losing 1 electron. The change in oxidation number is by 1, and again, there's 1 atom, so 1 times 1 is 1. But again, my reducing agent loses electrons, so it's a product. All right. Now, I'm done the half reactions. I want to put it together to write a net reaction. So what I have to do is balance my electron transfers. I have one electron being gained and one electron being lost. That balances. So they cancel each other out, and my net reaction becomes lithium ions plus sodium solid atoms, or solid metal, whatever you want to call it, becomes solid lithium metal and a sodium-free dissociated dissolved ion. Okay? So those are your steps. Identify your half reactions and then write your net equation. Okay? Let's look at another example. When you have an equation that's already balanced, I usually just ignore the balancing coefficients. They will come back when we write the net reaction, and I'll show you that in a second. But usually we just want to think of what's happening on the individual, each half reaction. So I'm starting again with elemental zinc as an atom, and it's reacting with gold nitrate. Now, nitrate polyatomic ion is -1, and there's 3 nitrates balancing with my gold. So that means my gold must have a 3 positive charge. Again, these are now ions because they're part of an ionic compound. Gold on the product side is now by itself, so it's now in its atom form. And then zinc is bonded to 2 nitrates this time. Nitrates again being -1, so zinc must be +2. Okay? My spectator ion is the nitrate. The nitrate is starting as -1 and ending as -1. Now, my gold oxidation number is going down from +3 to 0. So that is, again, the OAGER, the oxidizing agent, which will be gaining electrons undergoing reduction. And my zinc is starting as 0 and increasing to +2. So my oxidation number increasing means this is my RALEO. So again, remember what this means. Oxidizing agent gains electrons, undergoes reduction. Reducing agent loses electrons, undergoes oxidation. So if I write my half reactions again, and it doesn't matter the order you write your half reactions in, I usually start with my oxidizing agent undergoing reduction, but it doesn't make a difference. Okay? So I'm starting with free dissociated gold ions with a 3+ charge. Right? That's what I have on my reactant side. And on my product side, I have gold solid. Okay? So again, if I'm looking at what's happening to my oxidation number, it's going from +3 to 0. So it means that it's gaining 3 electrons. Going from +3 to 0. Again, if you want to write that here, my number of electrons was my change in oxidation number, which was 3. And again, there's 1 gold. Remember, we're ignoring those balancing coefficients to start. So there's 1 gold on each side. So it's 3 electrons that are being transferred in the gold half reaction. And they're being gained because the oxidation number went down. Now my reducing agent, which is undergoing oxidation, is zinc. Zinc is starting as a solid metal, and it is turning into free dissociated zinc 2+ aqueous ions. Now the number of electrons for my zinc half reaction, zinc is starting as 0 and going to +2. So the change in oxidation number is 2. And again, if I look at this half reaction I have down here, there's 1 zinc on each side. Okay? We don't show those ones, but that means there's 1. So my change or transfer in electrons for my zinc half reaction is 2, and it is losing electrons, which means the electrons are a product. Now, I'm going to write the net between these two. But notice how the electron transfers no longer balance. I have to make them balance. What is the first common thing I can get them to? That would be 6. So I'm going to have to multiply the gold half reaction by 2, and I'm going to have to multiply the zinc half reaction by 3. So this will become 2, this will become 6, this will become 2, this will become 3, this will become 3, this will become 6. So now my electron transfers balance. You always find the lowest common number that you can get those two for balancing coefficients, because you always want to use the lowest whole number balancing coefficients. So my electrons cancel, and my net reaction is 2 gold 3 plus aqueous plus 3 zinc solid produces 2 gold solid plus 3 zinc 2 plus aqueous. Okay, notice how those balancing coefficients matched what was up here, right? We had a 3 in front of the zincs and a 2 in front of the golds. We do it later on by balancing the electrons to get those coefficients. But we start with each half reaction with 1 atom. If they're not diatomic, we start with them as 1 atom. Okay, one more example, and then I think there's a practice diploma question. And then that's it for this lesson. This time, my single replacement reaction is going to be the element bromine. That is a nonmetal. So when it switches places with an element in the ionic compound, it will be the other nonmetal, which is iodine. So iodine will be by itself, and the bromine will go with the sodium. Okay, now this reaction's already given, so you don't have to write that, but if you didn't, you would have to write that. Now again, we still start with oxidation number. Bromine, even though it's diatomic, it's still in its atom form when it's by itself. It's only an ion when it's part of an ionic compound. Okay, my iodine by itself is 0, and my sodium bromide is now ions because, again, they are in an ionic compound. Now, my sodium is my spectator ion. The sodium is the one that starts as +1 and ends as +1. So that is my spectator ion. My iodide is going from -1 to 0. That's an increase in oxidation number. So this is my RALEO. And my bromine is going from 0 down to -1. That's a decrease in oxidation number. So that is my OAGER. Okay? Now we're going to write these half reactions again. So I'll start with my oxidizing agent undergoing a reduction half reaction. That's my Br2 that starts with an oxidation number of 0, and it is producing bromide with a -1 ions. Now, this is where, before I figure out my electrons, I need to make sure I have equal number of bromines on each side. Bromine is diatomic, so there's 2 bromines in that molecule, which means I need 2 free bromide ions. Okay, that's why I'm putting a 2 here, because bromine individually by itself is always diatomic, so it forms 2 free bromide ions. Okay, so my number of electrons being transferred, I'm going from 0 to -1. So the oxidation number change is 1, but there's 2 atoms of bromine on each side. So that means we are gaining, because again this is reduction, 2 electrons. So my 2 electrons are going to be a reactant. My other half reaction for my reducing agent that's undergoing oxidation is iodide. My iodide is starting as a free ion, and it's turning into I2 as an atom or a molecular diatomic element. Okay? Again, this is diatomic. So if two iodines come together, I need to start with two free iodide ions. Okay? And so my number of electrons being transferred here again, the change is from -1 to 0. So the change is by 1. But again, there's two atoms in that half reaction that we just wrote. So I have 2 electrons being lost because this is oxidation. So my 2 electrons are a product. Notice again, every time you write a net redox reaction, one species is gaining, one is losing. One is a reactant, one is a product. Now they cancel here. There's 2 on each side. So I don't need to multiply the half reactions by anything. I can just cancel the electrons and put everything together. So my Br2 liquid is reacting with 2 iodide ions to form 2 bromide aqueous ions and I2 solid. Okay? Now, as I said, I think there's a sample diploma question. Notice how I highlighted this. When you guys are writing tests and quizzes and diploma exam, you should always highlight the key terminology that it's looking for. It's asking for the reducing agent in the following reaction. Now, something I think I forgot to mention is agent means reactant. Okay? So the products will never be an oxidizing or reducing agent. So right away, you can cancel out the products. Now, the reducing agent. Remember the saying we have is RALEO the OAGER. So reducing agent is the RALEO half reaction. That's what RA stands for, reducing agent. That happens to whichever species oxidation number is increasing. So that's what we need to do for this reaction. We need to look at oxidation numbers and look at which one's oxidation number is increasing. So iron here is starting as 0. My hydrogen is in an ionic compound, so it's +1 and the chloride is -1. Iron is turning into an ionic compound, so it's turning into ions. There's 2 chlorides, each chloride are -1, so that means the iron must have a charge of +2, and then hydrogen turns into an atom on the product side. So which one's oxidation number increases? The iron. The iron is going from 0 to +2. So that is my reducing agent, meaning HCl would be the oxidizing agent. And these terms, reducing agent and oxidizing agent, are going to come up a lot in the next lesson. So it's important to know, again, the difference. So our answer for this would be D. All right? That is it for this lesson. Thank you for watching.